Perfect. So, welcome everyone. It's a great pleasure to have here Nils Schöneberg today. Thanks a lot for accepting our invitation. Nils is a Maria de Metzu postgraduate research fellow at ICC University of Barcelona in Spain, and before that he got his PhD in Aachen in Germany. Nils' research topics include the work on the cosmological tensions, such as the H0 Olympics paper and the Tale of Many H0 review, as well as the work on the Big Bang nucleosynthesis and baryon abundance. Today he will present recombination solutions to the Hubble tension. Is there still hope? Nils, you can start please when you're ready.
Thank you very much. And also thank you for the very nice invite to this excellent CosmoVerse series of seminars. As you presented, my talk is about recombination solutions and whether there's still any hope for those. So let's establish a baseline, first of all. We are going to quickly look at the Hubble tension, and I know you're all very much experts, so let's make this review very, very brief. So we have, on the one hand side, we have the local distance ladder measurement of the Hubble constant, which is based on the recession velocities of galaxies. And we basically use the Hubble law, though of course nowadays we have something slightly more sophisticated, which compares the observed and the intrinsic magnitudes of objects to give us the luminosity distance, where the luminosity distance scales inversely to the Hubble parameter, and this is how you get it. What we typically need is to calibrate this intrinsic luminosity using some kind of standardizable bright object, which we typically call a standard candle. And the value of the Hubble parameter that we get out of this procedure is around 73 plus minus 1 kilometer per second per megaparsec. On the other side, we have the cosmic microwave background, where we measure the anisotropies. And more particularly, we measure these kind of angular sizes of these little patches in the sky, where these little patches correspond to some physical imprint of some underlying standard ruler, in this case, the sound horizon of the baryonic acoustic oscillations that happen in the early universe. And the angular size under which we observe it is simply related by geometry. In the small angular approximation, we simply get that it's the ratio of the sound horizon and the co-moving angular diameter distance. Now, the co-moving angular diameter distance is inversely proportional to the Hubble parameter, giving us overall this measurement of the Hubble parameter that you very much know of around 68 plus minus a half kilometer per second per megaparsec. And I want to quickly focus on this expression for the sound horizon, more precisely angular sound horizon. And let's look at that expression and let's express slightly further the angular diameter distance. So as most distances in cosmology, it's written as the speed of light times the time, in this case, the conformal time. And we can re-express it in terms of the redshift. And we can express the Hubble rate as a Hubble constant times some kind of expansion rate. And we can plug this back into the original expression to get kind of a more comprehensive expression for the angular size of the sound horizon, which involves in the numerator the two fundamental constants at play, namely the Hubble constant and the sound horizon as the calibrator. And on the bottom, it is kind of the relation, this kind of expansion integral that we need to do. Okay, so if we now look at some kind of patch of the CMB in the sky, we have a certain angular size of our sound horizon. What happens to this patch if we increase the Hubble parameter, where we know that the angular diameter distance is inversely proportional to the Hubble parameter, so the whole picture comes closer to us. It moves towards us. So angularly, it looks now much bigger. And this is a problem because this kind of sound horizon is very, very well determined by the CMB. So somehow we have to make the angular size smaller again. And our immediate naive reaction might be to just say, okay, if I pull the picture closer to us, I can just push it back, right? So this would be the idea of restoring the distance of the picture. And in this case, this means restoring the angular diameter distance. How can we do that? Well, by decreasing the expansion rate, as you can see from the formula that we've derived. If we do that, then the overall sound horizon angle will remain the same. And so does that work? How do we decrease the expansion rate? Well, at redshift 0, this is of course mathematically impossible, as we saw from the factorization. However, maybe at earlier times this is possible. In general, in late times, you can expand the expansion rate simply as the square root of some matter in the universe and some dark energy. And we neglect radiation since we are at late times. And here we see that if we want to decrease the expansion rate, we have to decrease also the amount of dark energy in the universe. But this is actually somewhat difficult for earlier redshifts, because this requires us to go to a phantom regime of the equation of state, i.e. the equation of state less than -1. And this we can simply see from, for example, the expression of the dark energy density that we would derive from using the conservation equation, an explicit integral representation. There's also an additional problem, which is that late time data very much constrains this expansion rate. So I'm now going to show you some results that I cooked up very shortly before this talk. So we have on the left-hand side the results from Pantheon supernovae and from the SDSS BAO. And I'm going to simply assume for now that the sound horizon is fixed because we're talking about late-time solutions. And I'm going to propose two different models, one with a Hubble parameter of 68, one with a Hubble parameter of 73, where I use the same omega m. This is the blue and orange line. And I'm also going to use a green line, where I now also include some dark energy variations. Right now, it's fixed at order 0, so there's no change. And you can see that the chi-square of this fit of the high Hubble parameter is very bad. And now if I try to make my dark energy model more and more flexible, at some point, my chi-square goes down and down, but plateaus out. And I find that I have an equation of state, which is less than -1, which is not great in and of itself from theory reasons, but I also find that the delta chi-square plateaued and it doesn't really go to 0. So there seems to be something bad. But maybe it's because I fixed the matter density. Maybe you have to also change the matter density. So let's do the same experiment again, now changing also the matter density. You can see that by default, this already decreases the delta chi-square, even if I don't have a fancy dark energy model. But now I start to run the same process again for increasing the order of expansion of some dark energy model. And once again, I run into a plateau. Here I only show up to order 3, but you can go up to order 6 or 10 or so, still the same result. So the delta chi-square is only around 60 again, which is very confusing. And we again have this W less than -1. So what's going on? This, I think, is very well summarized by this plot of Polar et al., where they describe the cosmic calibrator tension. And this is what I'm going to note now, that we have to change the calibrator. In this plot, it might be at first a little bit confusing, but let me tell you. So there's BAO and supernovae in this plot, in the same plot. How do we do that, first of all? Well, the supernova measure the luminosity distances, the BAO measure the angular diameter distances. And by using photon conservation, we can make a relation between the co-moving angular diameter distance and the luminosity distance, which allows us to put both on the same plot. And now we're using SHOES, or the local distance ladder, to calibrate the supernovae, giving us this blue line down here. And we're now, since we are talking about late-time solutions to the Hubble tension, we are fixing the sound horizon to the value determined by Planck, which gives us the BAO up here. And you can see that on the same redshift range, these two data are now discrepant. And so you will never find any model that can nicely fit the two if you don't allow one of these calibrators to break. You either have to break the SHOES calibrator or the Planck calibration of the sound horizon. So let's now think about another way of solving this problem. We have pulled the image closer, but maybe instead of pushing the image back, instead we make what is painted on the image smaller, because if we do that, the angular size of what is painted on the image will still be small. And this is the idea. You increase the Hubble parameter, and you correspondingly decrease the sound horizon, and then what you're left with is an angular size of the sound horizon, which does not change. So this is great. So let's talk about this weird quantity, the sound horizon, which is basically an integral from basically the Big Bang until the conformal time of recombination of the sound speed times the conformal time. So that's a very nice formula. And we can also rephrase it in terms of redshift, as we've done before for the angular diameter distance. And in this case, you find that there are basically three things involved. It's the sound speed, the Hubble parameter, and the redshift of recombination. Now, the sound speed is very difficult to adjust in a model where you don't also screw up all of the nice way that the BAO is imprinted in the CMB. So this is actually very hard to do. But there's two things that you can play with more easily, so to say, which is one, the Hubble parameter. And this is typically related to, for example, dark radiation solutions, which try to increase the amount of radiation in the early universe, thus increasing the Hubble parameter, or the early dark energy solutions, which put an additional amount of dark energy, which means just some additional stuff to increase the Hubble parameter in the early universe, and all of this is going to decrease the sound horizon. On the other hand, you might also think about the integral bound, which is the redshift of recombination. If you increase the integral bound, then you're going to decrease the interval over which there's being integrated, and thus you're going to decrease the sound horizon. And that's the idea of these, what I call the advanced recombination solution. For example, there's primordial magnetic fields in the early universe, there's fine structure constant variations or electron mass variations, and all of these kind of play with the same mechanism. So early exploratory work in Xiang and Souza in 2018 showed that this should be possible with a phenomenological model study, where they just varied the redshift of recombination and just looked at what happens in terms of Planck data. And they found that high values of the Hubble constant can very much well be reached in this kind of model. But the question is, how do you generate such a model? And the answer came just a little bit more than a year later by Liu et al. In 2019 with this paper of Can Non-Standard Recombination Resolve the Hubble Tension? And there they investigated what you would need to do to recombination to actually shift the redshift of recombination. And it turns out the redshift of recombination is basically already given by all of the atomic physics that's going on in the early universe. There's not really a lot of cosmological model dependence in there. And I want to quote from their conclusion: the Hubble tension is very robust against perturbations of the recombination history, unless exotic physics somehow modifies the atomic constant during the recombination epoch. And so this, of course, got theories to think, well, what if we modify such constants? And I'm going to guide you through the step by step by using first a very simple argument. So the binding energy of hydrogen, as you very well know, is simply a half times the electron mass times the fine structure constant squared, which gives you the approximate value that you know from undergrad studies of 13.6 electron volt. And if you want to now estimate the redshift of recombination, the first naive approach would be to say, well, all the photons should at that time have the same energy as the binding energy, which would give you this naive ratio of the binding energy to the CMB temperature now as the redshift of recombination. However, that's not quite the case in this case, because you have a lot more photons than there are baryons. So you get this very small baryon to photon ratio, which in the Zaha approximation gives you an additional factor of around 1/4T, simply because there are so many less baryons. And then additionally, this whole process is a non-equilibrium process, which still corrects this value of the recombination redshift down by another around 75%. And this in total gives you around a redshift of 1080 for recombination. But the most important part is that it is still proportional to the binding energy. So if we can propose a mechanism to vary alpha or ME, we vary the binding energy, and thus we solve the Hubble tension. Well, is that the case? Because, well, this argument is very nice and wishy-washy, but it only works at the background level. But most solutions to the Hubble tension fail actually with the perturbations and not at the background level. So let's look at the constraints that you get for one of these models, which is the varying fine structure model. And already in 2019, it was clear that this model does not work. So here we see Planck 2015 and Planck 2018 data in the Hart and Kluwer paper, and they got constraints of the level of 5 times 10⁻⁻3. So actually, surprisingly, this is not a good solution. But why is this the case? As we're going to see, this relates to Sigg damping. But let's come back to that point, because I want to make sure that this model is dead as a doornail. So I'm going to put a nail in the coffin, because we asked ourselves in a very recent paper if the model can be revived. So my good friend Leo Bacher and I set out in 2024 to think about, well, maybe how can we think of getting constraints on this model which aren't even dependent on kind of cosmological data. And we found that there's a generic bound on the variation of the fine structure constant, which is even stronger than that at the CMB, namely at the level of 5 times 10⁻⁴, applying to non-fine-tuned single scalar field models of this kind of variation. And the reason why I'm telling you this is because I'm going to recycle it for the electron mass, and also because it's just super instructive and interesting. So the idea here is simply to use the Klein-Gordon equation for scalar fields, and these scalar fields are going to cause, in the end, the variation of the fundamental constants. And the Klein-Gordon equation, you can simply integrate. It's a very trivial equation, and you get a homogeneous solution and a particular solution. The particular solution involving the potential slope we're going to look at later. But let's focus for now on the homogeneous solution, which is telling us basically that there's a speed limit to how fast a scalar field can slow down. Indeed, a scalar field in general, and this we show a little bit more in the paper, cannot slow down much faster than a⁻⁻3. And now the idea is, okay, let's look at some kind of scalar field that somehow generates a variation of the fine structure constant. Let's say, for example, with the linear coupling. In the paper, we also look at more complicated couplings. And this kind of relation means that the amount of fine structure variation is given simply as some coupling times the field change, and the field change is simply the field speed, in this case, the logarithmic field speed integrated over the logarithm of the scale factor. And similarly, the variation today of the fine structure constant, the current speed of this variation, will also be given by the field speed, in this case, with respect to the logarithm of the scale factor, also multiplied by this coupling constant. Now, the crucial thing here is that both of these are proportional to this coupling constant. So this means that their ratio will be independent on the coupling constant. So no matter how strongly or how weakly you couple the field to the fine structure constant, if you want a certain delta alpha over alpha at recombination, you're going to have a certain field speed today. And that's the kind of whole idea. So let's say we want some cosmologically relevant delta alpha over alpha at recombination, which puts us in the order of 1% or a little bit more in order to have a significant change of the Hubble constant. However, there are also constraints on the current field speed because there are constraints on the current variation of the fine structure constant. Namely, these come from atomic clock constraints. And so this means that we have to bridge somehow 6 decades of deceleration. And now let's look at the expression for the logarithmic field speed, which is simply the field speed over the Hubble parameter. And we insert this kind of h to the minus 3 scaling of the field speed that we can have at most. And for the Hubble parameter, we know that, for example, in meta-domination, it scales like h to the minus 3 halves, which means that the field can only slow down, this logarithmic field speed can only decrease approximately like h to the minus 3 halves. Is that enough? Well, we only have 3 decades of time from redshift around 1080 to today with a speed of 3 halves, which gives us only 4.5 decades. So it's impossible to get these 6 decades of deceleration that we would need. Well, if you make this argument a little bit more robust and a little bit more careful, you get a factor of around 10 to the 4.7 instead of 10 to the 4.5, which roughly translate to a factor of 5 times 10 to the 4. And so we kind of couple the amount of fine structure constant variation at the CMB to that nowadays observed in laboratory experiments with atomic clocks. And if we put in this 10 to the minus 8 bound from nowadays, you get an overall bound on the CMB fine structure variations of 10 to the minus 4, which is even stronger than that of the CMB. So we're using data now to constrain stuff at the CMB, which I find kind of wild. Okay, I told you that we would also have to deal very quickly with this kind of potential slope, which is in the particular solution. Well, what you have to realize about this part is that there's a weighing factor, namely this a cubed over h that we have here for the potential. And this weighing factor is actually very tightly peaked. So it goes around like a to the 4.5. And this means that only the scale factor is bigger than around 0.2, which corresponds to a redshift less than around, let's say, 8. Actually manage to make any difference on this overall integral. So you have to adjust the potential slope, not just anywhere, but kind of exactly today to exactly the right value to cancel out all the velocity that you've accumulated before. And so this is just an extreme degree of fine-tuning, which will typically in Bayesian analyses be completely disfavored by the data. So, because it will not have a good prior. So let's come back to this idea of constraining the kind of solutions with Planck data, for example, with CMB data. Is the same problem also there for the electron mass solution? And there, surprisingly, we find that this is not the case. In Hart and Kluber, this was already shown in 2019, so 5 years ago, that with Planck 2015 or Planck 2018 data, you have a very broad range of electron mass variations that are still allowed, corresponding to a very broad range of Hubble constants that are still allowed. And similarly, in 2021, in our H0 Olympics paper, we found very similar results, namely that the varying electron mass solution was one which was among the top contenders. And then there was this very surprising result, which baffled me for a long time after, which is that if you add a curvature on top, that suddenly the solution does not just become one of the better solutions, but it becomes the best solution that we investigated in the whole paper, meaning that to date, it's still the best solution for the Hubble tension that we have come up as theorists. And this is kind of mind-boggling for me. So why is it that this solution is not excluded? Well, the first hints already came in Hart and Kluber 2017 and 2019, because Kluber always is first in everything. So there we had the scaling of the binding energy and the scaling of the Thomson-Kettering cross-section, and they were different for fine structure and electron mass. And this kind of already kind of hinted at what might be going on. But the real analytical argument, the complete analytical argument, only came by Sekiguchi and Takahashi in 2020. And I'm going to quickly reproduce it here because it's going to be super instructive also for all kind of early recombination solutions. So let's think about what these kind of solutions have to do. Well, at the CMB times, we need two big things. We need the baryon to photon and the matter to radiation ratios to be the same independently of whether we change the redshift of recombination. Why is this? Well, because both of these kind of directly imprint in the angular power spectrum of the CMB. The baryon to photon ratio imprints in the even to odd peak ratios, and the matter to radiation ratio has a direct relation to the gravitational boost of the baryon acoustic oscillations, which imprints in the height of the first versus the second peak, for example. And so we want both of these to stay the same. So let's look at these expressions. So for example, here we have the baryon loading, which is essentially the baryon to photon ratio. And the baryon loading is basically this ratio of the physical baryon density divided by the physical photon density times the scale factor. So now we write it down at recombination, and we simply required at recombination, this should always be the same independently how I change, in this case, the redshift of recombination, which I now specify through the scale factor A star, which is the scale factor of recombination in what I'm going to talk about. So you don't want to touch the physical amount of photons because this is very well measured from all of the experiments that measure the CMB photons around us. But what you can try to do is change the physical amount of baryons around us. So what we do is simply we say, or we impose that the amount of baryons should scale inversely to the scale factor of recombination. This is going to be our first law. Let's look at the matter to radiation ratio, which follows a very similar argument. You can write down the expression. You can ask it to be constant at recombination, which again, you can either scale the radiation content or the matter content. Let's say we don't touch the radiation, we leave the neutrinos the same, we leave the photons the same. So then we have to change the matter. And so this would give us that if we want to increase, for example, the scale factor of recombination, we have to decrease the amount of matter in the universe. Okay, so these are our two fundamental laws that we have now derived. And now let's think about all the different scales that are in the CMB. And what I'm going to show is that this is already sufficient that all of these scales behave very nicely. So let's first think about, for example, the sound horizon. This is the fundamental thing that we are trying to change. We are trying to decrease it. So let's write down the sound horizon again, and we expand it again in terms of redshift. And now we explicitly put in the formulas for the sound speed and the Hubble parameter. The sound speed is given by this 1/√3 modified with the baryon loading, so 1 plus r, which is the baryon loading. And the Hubble parameter is basically given as 1/√, of matter density plus radiation density, which are the only two densities that really matter this early, before recombination. And the matter and radiation density, we can factor out the radiation density, giving us a ratio of the matter to radiation. And oh, we already know that that is supposed to be constant by shifting recombination, which is our orange box here. And similarly, the baryon loading by our green box is also supposed to be constant. So let's ignore these two terms. These are not supposed to change. So this only leaves us basically with the radiation density. And now it's all very simple algebra, right? You plug in the expression of how redshift relates to the scale factor to convert this integral to a scale factor integral, and you plug in the relation how the radiation scales with the scale factor. So you plug all of this in, you cancel like terms, and then you are left with an integral which happens to evaluate exactly to the scale factor of recombination. So overall, the sound horizon happens to be exactly scaling with the scale factor of recombination. That's not only a very pretty result, but this is also, of course, the reason why we're investigating this in the first place. In the first place, we're trying to find something that decreases the sound horizon. So of course, it's very good that now if we decrease the redshift or increase the redshift of recombination, decreases scale factor of recombination, that we indeed decrease the sound horizon. This is the whole idea. What about the other scales? So there's two more scales that we should care about, the equality scale and the damping scale. So for the equality scale, we can play the same kind of game. The equality scale is inversely proportional to the wave number equality. The wave number equality is defined as the wave number that enters the Hubble horizon at quality. So we can replace it with the co-moving Hubble horizon. And the co-moving Hubble horizon, we can once again expand as matter plus radiation. So I'm going to write it down explicitly. We know that equality, the both should be the same. So we can replace it with 2 times one of them. I'm going to choose radiation. And now the interesting thing is that I'm not going to change the amount of radiation, this I have said before. And what's left is only the equality scale factor. So all of this means that the R equality is directly proportional to the scale factor of equality. But wait a moment, this is not quite what we wanted, right? We wanted the expression involving the scale factor of recombination. So what went wrong? Well, nothing went wrong. We just have to do one more step. The scale factor of equality is defined as such that the radiation and matter densities are the same, which gives us this very well-known expression for the scale factor equality. But now if we apply our scaling laws, we know that the radiation doesn't scale, and the matter scales inversely to the scale factor of recombination, which means that the scale factor of equality now scales directly proportional to the scale factor of recombination. And thus we can put everything to rest, and we find that the scale of equality happens to vary exactly in the same way for any kind of solution that tries to change recombination. So this is great. Now we have 2 of the 3 important scales of the CMB. What about the third scale, the damping scale? Well, we can play the same game, but this time the game is a little bit more complicated because the expression is a lot more involved. And I'm going to simply refer you to the result by Sekiguchi and Takahashi in 2020. And what they showed is basically this big expression. And I'm going to do now a little bit of a simplification. I'm going to say the helium does not change drastically. So I'm not going to change drastically BBN. And this omega B here, the amount of baryons, I'm going to use our green scaling. So with that, I find this expression that the damping scale should scale as the scale factor of recombination squared divided by the square root of the Thomson scattering cross-section. And this is almost what we want, except for this additional factor of A star over the square root of sigma t. So that's kind of a bummer. We set out to prove that all these scales behave nicely, and this one doesn't really. So we can ask ourselves, is there maybe a relation between the scale factor of recombination and the Thomson scattering cross-section? And for this, I go back to the original scalings that we discussed of the binding energy and the Thomson scattering cross-section. And now the nice thing is that the redshift of recombination is, of course, proportional to the binding energy, as we have talked about before. And 1 over the scale factor is, of course, proportional to the redshift. And therefore, we have a relation between the scale factor of recombination and our fundamental constants. And our fundamental constants also appear in the Thomson scattering cross-section, meaning that for each given model, either alpha variation or ME variation, we can check how the A star relates to the sigma t. So let's do that explicitly. In the alpha model, in the fine structure variation model, we get that the redshift, the scale factor scales as alpha to the -2 and sigma t as alpha squared, which means that sigma t scales inversely to A star, which is not what we want. This is not going to cancel anything out. That's very bad. However, in the electron mass model, we find that the scale factor varies inversely to the electron mass, and the Thomson scattering cross-section inversely to the electron mass squared. And this happens to be exactly such that the Thomson scattering cross-section is proportional to the scale factor of recombination squared, which exactly cancels our term. So by happy coincidence, by happy magic, this exactly means that the damping scale of the CMB is left in the same kind of very simple law as all the other scales of the CMB for the varying electron mass model. And now we also see the difference to the varying fine structure constant model. Now, we are not quite done yet because we observe the CMB, and thus we don't observe the real physical scales in the sky, but actually only the angular scales under which we see it. So we have to divide each of the quantities by the angular diameter distance. If we want each of these quantities to stay the same, then we get an additional condition. The angular diameter distance should now also scale as A star in order for all of these angular ratios to remain fixed completely. And then the CMB will left invariant no matter what A star we use. So let's write down explicitly the expression for the co-moving angular diameter distance. And since we're using an early time solution, let's not assume that the late time is very different from lambda CDM. So we're going to again have some physical matter, and we're going to have some dark energy in there as well. And now what we're going to do is we're going to use that formula to derive a relation between how the Hubble parameter has to scale in order for the angular diameter distance to scale as we want. And so now we have found indeed a solution. If we scale the Hubble parameter according to this prescription, the CMB is indeed left completely invariant, and any value of the recombination redshift is possible. We can reach a Hubble parameter correspondingly as high or low as we want. And this is also what we saw in the Hubble Olympics paper in 2021. If we use a Planck CMB data, we find that any value of the Hubble parameter is allowed. We find this very slight preference for lower values, but not really a good constraint. But this is only using CMB data. And now we add again BAO data. And suddenly we get a tight constraint. Why is that? I thought that we were playing around only with these angular scales and that it was supposed to leave everything invariant. What happened? And so let's go back to our nice picture. Well, we change the calibrator, and in principle, the sound horizon should be left the same by this. So this should also apply for the sound horizon of the BAO. Why does it not? Well, we changed one particular thing, which is we changed the fractional matter density as well. And this we shouldn't have done, because this is actually changing something in the late time dynamics. Without wanting to, we changed the late time dynamics. And this got us to have conflicts with the BAO data. So let's see how this worked. Well, we imposed that the Hubble parameter should change like a star to the minus 3.23 in order to get the angular diameter distance to work out. But we also imposed that the physical matter density scales as a star to the minus 1 in order for the matter to radiation equality to work out. And now writing down these and using the expression for the fractional matter density as the physical matter density divided by h squared, we can very quickly just plug in numbers and see that there is a scaling of the fractional matter density necessarily when we use these kind of solutions. And we can even relate it to the Hubble parameter by using this law up here to do one last proportionality. And we find that that should be a proportionality. The matter fractional density should be proportional to h to the minus 1.7. And so that is somewhat of a universal law for early recombination solutions. So let's see if this universal law is indeed universal. So for example, let's try to imagine a model where we don't just have a constant shift of the electron mass, but let's just say, okay, now we're going to allow arbitrary functional shapes of the electron mass as a function of the redshift. This we did in Lee in 2022. And what we found were some certain shifts of h and omega m. And they were, for example, if we wanted a 7% upward shift to solve the hypertension, we got an 11% downward shift to for the fractional matter density. And if you relate these, you actually find exactly the scaling that I talked about before, this kind of universal scaling prediction. And similarly, in Lynch in 2024, they did a freeform reconstruction of the ionization history. And let me guess what is the degeneracy direction of the cold dark matter versus H0 plane. This exactly turns out to be such that the fractional matter density scales as h to the minus 1.7, this universal law. So this is kind of a universal scaling law for any solution trying to work with changes of recombination. And you can even show this for arbitrary freeform reconstructions. So that's a problem. We go back to our drawing board and we see that varying electron mass solution seems to be defeated. But then we remember our H0 Olympics paper. We remember that adding the curvature somehow improved this solution a lot. So this is the effect of adding curvature. You see two effects. One, the red contour jumps around slightly to the side, and two, the orange contour gets blown up a lot. Now for the red contour jumping from side to side, there's a simple explanation. The Planck likes slightly negatively curved spaces, whereas the BAO constrains the curvature not to be too negative. And so it actually turns out that this addition of a curvature moves you to the top right in the H0 omega m plane. And if you include BAO, you are basically back to zero curvature. However, more importantly, you also get this very much broadening of the contours. And why is this? Well, there comes double effect. One of the effects I've already figured out quite early, which is that the curvature confuses the BAO and supernova data. Simply, you don't just have to constrain omega m with these data, but you also now have to constrain omega k. So they have more stuff to do, which means that each of the constraints is going to be less strong, allowing your model more leeway. But there's also another effect that I only realized later, which is that the curvature also breaks your direct relation between the Hubble parameter and the redshift of recombination. Why is that? Well, because you don't now have to adjust your angular diameter distance under the assumption that your late time history is always the same, but you can adjust your angular diameter distance in a way that it exactly scales like a star with two additional parameters, with h and omega k. And this allows you more freedom to do this. And so what we find is that this works well enough for current constraints. This works in the sense that we can reach very high values of the Hubble parameter, and we have an excellent solution of the Hubble tension. How do we get rid of this solution? because this is what the whole research should be about, getting rid of strange theoretical solutions. Okay, so let's first try to think about, well, what can we use? Well, let's imagine this single field kinetic constraint that we used for the alpha. This was one of the most precise constraints, and it was very model independent. And sadly, my colleague Leo Vachea tells me that this is not possible. In a recent paper in 2024, we investigated whether this was possible, and we looked at the fine structure constraints not only on the alpha, which is the atomic clock constraints, not only on the alpha, which is the fine structure, but also on the ME, which is the electron mass. And it simply turns out that there is less sensitivity to the electron mass. We have a logarithmic sensitivity to the fine structure constant of 10 to the minus 8. For the electron mass, we only have 10 to the minus 6. And that's a problem. This comes both from a degeneracy, which with something that's called the proton magnetic moment, and also simply because these were older experiments that tested this with those precise configurations. And this means that overall, we get, with a factor of 5 times 10 to the 4 that we get from the single field kinetic constraints, we get a 5 times 10 to the minus 4 constraint for delta alpha over alpha, versus a 5 times 10 to the minus 2 constraint for delta ME over ME. And 5%, sadly, is not good enough to constrain the solution significantly. So in this case, I'm drawing on top of the H0 Olympics simply the contours. What would happen if we included this 5% constraint? And you can kind of see that this still allows all of the solutions kind of as before. So let's say the single field kinetic constraint is not really a viable way of constraining the solution. But maybe instead we can use more data, like, for example, the new DESI data. What about it? Well, if we use the new DESI data, first of all, we see that kind of the same thing is still allowed. So for example, here I'm using Planck plus DESI, P plus D, and I'm constraining either the electron mass plus curvature, or electron mass plus a W0, WA parameterization of the dark energy, which is also some other way of confusing the late time probes and allowing us to break away from this one-to-one scaling of the angular diameter distance and the Hubble parameter. And this, in this case, shows us that we can still reach very high values of the Hubble parameter in all of these models. And similarly, if you include also the Pantheon Plus data, once again, you find that this is still possible. So not even the Pantheon Plus supernovae disallow you to go into this part of the parameter space. So that's a problem. And then we looked at the constraints that we got out. And first of all, we were slightly confused because suddenly we find that there's like a 2 to 3 sigma hint of a variation of the electron mass in DESI data, which by itself is already interesting. But then we got even more confused because the Hubble parameter mean values, without imposing any shoes data or anything like this, were already quite high. Indeed, they are so high that we can report that with Planck 2018 data, with DESI data, and Pantheon plus supernova data, the varying electron mass plus curvature model has only a 1 sigma Hubble tension by default. So there's no kind of using shoes data or anything like this. So the Hubble tension is basically gone in this model. So, well, with shoes, we get a less than 2 sigma Hubble tension. That's great, but it also means that we haven't killed this model. And okay, so the DESI data doesn't help us. It even favors this model, which is kind of infuriating. By the way, the reason for this is, of course, that DESI prefers a somewhat smaller fractional matter density than all the previous SDSS BAO measurements. And in order to really be clear, we need to resolve a tension that currently exists between the supernova data sets, which require a higher value of this fractional matter density, and the kind of BAO data sets, which currently want a lower value of this fractional matter density. So, for example, the SDSS versus DESI has a much weaker impact on something like early dark energy, because early dark energy does not shift this fractional matter density too much. Let's now think, what is our last hope? Maybe BBN data can kill this model, right? Maybe that's our last hope. So what we did is we put in omega BA squared pi. Of course not. We try to go all the way. We try to implement a full pipeline of BBN where we have variations of the electron mass, allowing us to kind of capture the full effects of how an electron mass would impact, a change electron mass would impact the BBN. And what we find is that, well, the BBN constraints, the BBN only constraints, they are only at the level of 5%. Meaning that, for example, if we include DESI data as well, we find that the Hubble parameter can still go up well above 70 at the 1 sigma level and at the 2 sigma level especially. And if we now add Planck data again back into the game, we see that there's no big difference between Planck plus DESI or Planck plus DESI plus BBN data. Both of them still allow us to go to high values of the Hubble parameter. So this is kind of good news for the model, but bad news for us trying to get rid of it. Not even BBN data works. So varying electron mass is a little bit like a cockroach. We cannot get rid of it easily. With the extensions, it doesn't look much worse in terms of BBN. You might have thought that, well, maybe it doesn't kill the electron mass model, but it kills the electron mass plus curvature model. But this is also not the case here. I show Planck plus DESI plus BBN data. And if I use the curvature or the W0WA model, this still very much works out. So what are the challenges here? Well, we are going to very soon have future power spectrum data, which is going to measure both the fractional matter density through the BAO and the physical matter density through something like the shape of the power spectrum. We are going to have future BBN data and thus tighten the BBN constraints, especially from future deuterium measurements. And we are going to have future data of atomic clocks, which is going to tighten these kinetic constraints. So very soon, we should know one way or the other. And let me address a little bit of a criticism that I get often for this kind of model. Is the mechanism natural? And we might have some conceptual issues with variations of fine structure constant or electron mass. First of all, let me tell you that this is not that hard to do. It's very easy to come up with a scalar model, a scalar field model that is coupled to the electromagnetic or Yukawa terms. The electromagnetic one, for example, is almost a generic prediction of string theories. So it's not something that is super impossible. It's something that theorists, if they're creative enough, can come up with. And more importantly for me, as a more data-sided cosmologist, even if the precise mechanism turns out to be wrong, it tells you a precise story of what you gain and lose with these kind of early recombination solutions. So one thing is you find generic results for any early recombination solution, which, for example, is the scaling of the Hubble parameter, that you have to keep all of these scales in the CMB the same, and that, for example, only the electron mass can scale the damping sound horizon correctly. To summarize my talk, the late-time solutions are not currently favored. Varying constants are surprisingly efficient, while the large fine structure constant solutions are excluded. The electron mass solution survives and even thrives. And you cannot kill it with BBN, you cannot kill it with kinetic constraints, you cannot kill it with ZMB, BAO, or supernova data sets. So it's kind of like a cockroach. And the solution is currently apparently favored by DESI. We're going to wait for new data, but right now it predicts less than 2 sigma Hubble tension without including any shoes data. And new constraints are going to appear very soon. Thank you for listening.
Thank you so much. Very interesting talk. Do you have any questions, comments? Leandros?
Okay, thanks very much for the very nice talk. And I have 2 questions. The first question has to do with the hints for a possibility of alpha dipoles, which have been reported in the past. Later on, have been less. The initial 4 sigma tension has been reduced to much less. But in any case, it has not been ruled out. So it's a possibility to have, instead of having evolution of alpha, to have an inhomogeneity of alpha. Would this change something of your conclusion about the exclusion of the alpha approach? That's my first question. And my second question is, as you may have seen in my recent paper, if you only take one-step measurements of H naught, then the value of late-time solution of H naught becomes much lower. It becomes between 68.3 to 69 kilometers per second per megaparsec. So based on this data that I've shown, it seems that the Hubble tension is mostly based on distance ladder measurements and not on one-step measurements. I'd like to, so in that case, there would be no point to solve something that may not exist. I mean, if there is no real Hubble tension at late times, maybe there is no point to invent any early time solution. Could you comment on these 2 points, please? Thank you.
Yes, so for the first point, indeed, this kind of dipole in the alpha measurements, that has been very interesting. And kind of extending our formalism to include inhomogeneity would be the next natural step. For now, we assumed homogeneity because it's kind of the simplest assumption and kind of simplifies a lot of your equations. So we didn't yet check what happens if you use inhomogeneity. I know that there were some papers that kind of looked at this a little bit, and they found that that you could still get very tight constraints on the fine structure constant, even if it's inhomogeneous. but we didn't explicitly look at this in our current analysis. So if you want, you feel free to look at this. This sounds like an interesting topic. On your second point, I think that the one-step ladder of the Hubble constant is going to remain very interesting. It's a little bit, I think, early to make explicit conclusions because this is based on kind of modeling of the peculiar velocities, and we have to be very sure that we model those correctly. So I'm going to say that for now, I would trust the distance ladders really more because they kind of allow you to really extend far into the Hubble flow. But of course, the kind of one-step ladders are going to become increasingly important in the future. So I definitely see their value. Though right now, I would trust the three-rung ladder more than the one-rung ladder.
Let me just point out that in fact, the one-step part of measurements is a very diverse set of measurements, which includes also high Z. It doesn't include only very low, like the mega measures, of course, are very low Z, as you pointed out, and they depend somehow on the peculiar velocities, but most of the others are independent of peculiar velocities. Just a comment. Okay, thank you for your answer.
Thank you. Lloyd?
Thanks, Nils. I really enjoyed it. That was a great presentation. And I'm curious about for selfish reasons about prospects for ruling this out or providing more evidence for it from smaller scale measurements of the CMB. So to be coming soon from ACT and SBT 3G. And so your scaling argument would say, no, there's nothing in the CMB, but the sensitivity to when recombination occurs is one thing, but there's sensitivity to how that proceeds also. And so have you looked at forecasts of these models for? Or others looked at forecasts for these models of what one should see at at higher L in polarization and temperature anisotropies than what we have currently.
Yeah, you almost asked too good of a question. So this is something that I've been thinking about a long time, and I don't know yet the precise answer, but this is what I currently know. So I currently know that as far as the kind of damping tail that, for example, ACT is going to measure in the future goes, the primary thing that it measures is, of course, the damping horizon, which, as we have shown, is kind of invariant. And so that's nothing new. But as you say, we also measure kind of the effects beyond just the damping horizon, which is kind of exactly how recombination plays out, i.e. we measure effects like the two-photon rate and the Lime alpha redshifting rate. And these things are exactly this kind of non-equilibrium part that I had in one of my first slides here. This was this naive scaling argument. And basically the naive and the Zaha approximation arguments would be completely left invariant by this. But the question is, does this non-equilibrium factor here change, so to say? Because this non-equilibrium factor is given by these kind of two-photon rains and the Lime alpha redshifting of the photons. And these are effects that could be sensitive to in the higher L data of the ACT. And so this is something to look out for, but I haven't seen somebody explicitly forecasting this yet. So this will be interesting. I don't know the precise answer yet. Thank you.
So let's thank Nils again. Thank you so much.
Thanks to you. Bye.
Bye, everyone.